Alright, so in this video I'm going to be explaining this important article with the title DiffWire Inductive Graph Rewiring via the Lovasz bound. Lovasz is a great mathematician. He worked on graph theory, he got many awards, and many fundamental problems like commute time, many fundamental problems have been solved by Lovasz. Fundamental problems in graph theory. But these authors related his work to inductive graph rewiring. Because we do graph rewiring for over-squashing problems, and here they do it inductively using Lovasz bound. So graph neural networks have been shown to achieve competitive results to tackle graph-related tasks such as node and graph classification, link prediction, node and graph clustering in a variety of domains. Most GNNs use a message passing framework and hence are called message passing neural networks. Despite the promising results, message passing neural networks have been reported to suffer from over-smoothing, over-squashing, underreaching. Graph rewiring and graph pooling have been proposed in the literature as solutions to address these limitations. However, most state-of-the-art graph rewiring methods fail to preserve the global topology of the graph, are neither differentiable nor inductive, and require the tuning of hyperparameters. So, preserving the global topology of the graph is important. So, things like spectral graph theory, I have a playlist for spectral graph theory, and for example, calculation of commute time. For example, the eigenvalue, the gap, spectral gap, and those things are the core of these let's say global topological features. And we propose DiffWire, a novel framework for graph rewiring that is principled, fully differentiable, and parameter free by leveraging the Lovasz bound. The proposed approach provides a unified theory for graph rewiring by proposing two new complementary layers. The CT layer, a layer that learns the commute times. What a powerful thing. A layer that learns the commute time and uses them as a relevance function for edge reweighting. Well, it reminds me, for example, when you do the kernel, the graph diffusion theta I a to the I, where I goes from 0 to infinity. Of course, theta I decays to 0, otherwise it will produce an unbounded time series. So this provides a lot of information. For example, for a particular example of this is a to the k, when we have k regular graph. So these are important, but also, commute time, you can do it implicitly instead of this information, because what we get here is a n by n matrix, and it's a dense matrix. So we get the threshold and cut it, and then using for coarsening, that's another approach. But here, what they are using is a different approach, which is a commute time. Of course, it has correlation with these approaches as well, but they calculate commute time by learning, and they use it for edge reweighting. Of course, over-squashing is more overlooked than over-smoothing. Over-smoothing is rather simple if you understand a convolution. It's like a blurring filter that's blurring everything. But over-squashing is related to geometry, differential geometry, that bottleneck between a very lots of clicks and lots of clicks here. We have a bottleneck here. And it's different also from underreaching. So graph pooling and graph rewiring have been proposed to address these limitations. So Rewiring is a process of changing graph structure, but you know, when you're changing the graph structure, sometimes you, for example, I give you this click here is related with this link, which is very sparse, to another click. And so because of this, if we do rewiring, for example, connecting this and connecting this, you're changing the topology. So if you want to do graph classification, like protein, enzyme classification, DT dataset, MUTAG dataset, NCI1 dataset, there are many datasets. If you want to do, they because some of them, most of them, of course, sensitive to the topology of the graph. If you ignore this by rewiring, so it's a problem. That's why some researchers put a label here and say, okay, this edge that we have rewired has a label, so that in the process of learning, the machine understands to distinguish these things. So in the feature representation, the machine understands that these are added after the graph is given. So we should be very sensitive when we talk about graph rewiring. We cannot just add edges or nodes. We should do that. We respect the graph topology. So edge sampling based rewiring has been proposed to tackle oversmoothing and oversquashing. Oversmoothing may be relieved by removing interclass edges. However, this strategy is only valid when the graph is homophilic. Connected nodes tend to share similar nodes. So graph structural learning methods aim to learn and optimize graph structure and its corresponding representations at the same time. DiffWire could be seen from the perspective of GSL. And the graph, of course, there is a positional encoding literature, very long literature, is a feature that describes the global or local position of the node of the graph. So DiffWire is the method of this paper. The original graph from the collab, which is test set, and the center rewired. This one is the rewired one. Rewired graph after CT layer. Okay, so the Lovasz bound, first of all, there is a commute time between two nodes, U and V. For example, hit U and V is this one, hit V and U this one. If you add them together, it becomes the commute time. So let's say commute time is important. Commute time, if the distance between this one and this is upper bounded, which is by some variable that is related to spectral graph. And of course, this term is we call it effective resistance. I've explained it in spectral graph theory playlist. So they just use this important discovery of Lovasz bound, and they take advantage of that for spectral sparsification. Of course, these are classical things that this function is upper bounded between the when you want to. This is work of Spielman that I've explained in my playlist for spectral graph theory. Very classic thing. They had many ideas for graph coarsening, for example, solving linear equations. For example, as I remember, finding, for example, an expander, an algorithm for finding a good expander. Because if you have a good expander, it means that literally your oversquashing problems is solved. What can be better than an expander? Then every other node can be reached with very few number of hops. So it's very ideal. But of course it has computational complexity. So the commute times embedding, they just use that idea for embedding. That's it. So the spectral calculation of commute time distances is given here. So they saw this commute time as just an optimization problem. So constraining neighboring nodes to have a similar embedding leads to this one, which you're familiar with this in the previous videos that I've explained. Note that the above quotient of traces formulation is easily differentiable and different from trace of this in this reference that I explained. And so they define resistance diffusion, which is the Hadamard product between the resistance distance of the adjacency image. But you know, all of these is good, but you need to solve this loss. You need to do this learning. So it's just one layer. Then you repeat it. Just like hierarchical pooling. That you repeat a pooling network. So graph bottlenecks are controlled by this graph conduction. So we call it Shiger constant in graph theory. So given a graph, a subset, so we get a subset, again, some edges getting out, with volume of S. I mean, if you count the number of all the degrees of the nodes inside S, is less than volume of G divided by 2. It means that it is fair. Your S is fair enough. And then your trigger has a lower bound, and the number of edges going out has a lower bound. If this happens, then your effective resistance between two nodes is upper bounded for any pair. So it's very strong assumption. Topping proposed an approach for graph rewiring where relevance function is given by a Ricci curvature. I mean, one of the things that these methods will miss is that they don't care about the local structural things. Like, it's not obvious enough to see if, for example, it can also is related to expressive power of that. If it can count the triangles or the clicks inside the graph, or respect the higher order structures. For example, one click is connected to another click, or another click, higher order structures. These are missed because it's, you know, effective resistance is very global thing. It doesn't tell you about how it is achieved such thing. It's like a black box. It's like a conservative variable. I mean, there are infinite functions that their sum is 2. So you cannot say anything about f. You just say, okay, from infinite you have a subset of infinite, which is still infinite number of functions that provides this. You cannot say the same thing for effective resistance. You are saying in some topological thing which is global enough, but when you do the subtask, for example, graph classification, a graph classification is also sensitive to substructures. So how are you dealing with that? So you see, graph classification is really hard problems. And state of the art still are below 95%. Of course, some of them are still 70%, 80%. For enzyme, it's just 60-70%. It means that still we need to write articles to improve these state of the art. Rewiring using ratio cut approximation. We propose to rewire adjacency matrix so that lambda 2 is minimized. We consider a matrix A tilde close to A that satisfies this, where F2 is the solution of ratio cut. The gradient of lambda 2 with respect to each component is this. Then they do rewiring using this normalized cut approximation. So you get this idea. So now we have a gap layer R-cut. Again, they repeat this idea several times. So we have this architecture that we have rewiring here, then convolution, then min cut, then convolution. Then you can have a readout, finally your MLP. This is a CT layer or gap layer. In contrast to min cut baseline, which is just a min cut between the convolutions. So sort candidate by descending resistance. And then remove the head of the queue, update the current budget of edges. So the middle is the learned by the CT layer. You see, it is reducing the bottleneck by this rewiring.